Somewhere in our galaxy, a few stars are impossibly cold and dim. Astronomers have quietly wondered if they are stars at all. What if that faint glow was something built, not something born? A brand new study just gave scientists a real way to check. This idea did not start as fringe science. It started with physics. In 1960, physicist Freeman Dyson proposed something radical. A civilization could build a structure to capture a star's entire energy. Dyson first imagined this as one giant solid shell. Modern scientists now think that version is not realistic at all. Instead, they imagine a swarm of countless independent collectors. Each plate orbits independently, absorbing starlight for energy. This structure is now called a Dyson swarm. For decades, this stayed a purely theoretical idea. Then, in 2026, a new study changed the conversation. Physicist Amirnezam Amiri of the University of Arkansas led the research. The paper appeared on arXiv in February of 2026. It was later published in the peer-reviewed journal Univer. Amiri credits Harvard astronomer Avi Loeb with shaping this research. Loeb founded the Galileo Project, dedicated to searching for alien technology. This new study asked a very specific question. If a Dyson swarm existed, what would it actually look like from Earth? The swarm would absorb visible starlight almost completely. That energy cannot simply vanish. It has to go somewhere. It gets released back into space as pure infrared heat. That means the structure would look cold and dim to our eyes, but it would glow brightly under an infrared telescope. Astronomers plot stars using a chart called the HR diagram. It plots every star's temperature against its brightness. A Dyson swarm would sit in an unusual, mostly empty region. That empty region is exactly what makes it detectable. Amiri modeled this using real radiative equilibrium calculations. A larger structure would radiate its heat at a cooler temperature. That relationship gives scientists a predictable pattern to search for. But not every star is an equally good place to search. The study points to two specific kinds of stars: red dwarfs and white dwarfs, the remnants of dead stars. Red dwarfs make up roughly 70% of all stars in our galaxy. They burn fuel so slowly, they can last trillions of years. That is longer than the entire current age of the universe. That long stability makes them ideal for ancient civilizations. White dwarfs offer a completely different kind of advantage. They are the collapsed remnants of stars like our sun. They shrink down to about 1% of their original size. That means a swarm could orbit much closer to the star. Some models place the swarm as close as 0.05 astronomical units away. A closer orbit means far less material is needed to build it. So this research reshapes where astronomers should even look. But finding a candidate is only half the challenge. You also need a way to confirm what you are seeing. The study lays out a specific 4-part checklist. First, does the star show an unusual excess of infrared light? Second, does its brightness flicker in strange, irregular patterns? Third, is the signal missing the dust signatures real stars produce? Fourth, how does it compare against thousands of other known stars? This checklist only became practical because of a rare 20-26 alignment. 3 major observatories are converging around the same time. The James Webb Space Telescope handles detailed dust spectroscopy. The Vera C. Rubin Observatory tracks brightness changes over time. The Roman Space Telescope scans wide fields in infrared light. Together, these 3 tools finally make this search executable. And this is not a search starting completely from zero. In 2024, a project called Hephaestus scanned 5 million stars. It flagged 7 stars as genuinely promising Dyson sphere candidates. Every single one of those candidates was a red dwarf star. One candidate was later ruled out through careful analysis. A supermassive black hole was perfectly aligned behind it. That explained the unusual signal without any megastructure involved. But that still leaves 5 candidates completely unexplained. Those 5 stars are sitting in real data today. But this story has an important complication scientists cannot ignore. A separate 2025 study examined how long these swarms could actually survive. Around a white dwarf specifically, the news was not good. That tight, intense orbit is also incredibly unstable over time. A white dwarf swarm could collapse in about 0.00018 years. That is an almost instant collapse on any cosmic timescale. Swarms around smaller K-type dwarf stars fare only slightly better. Those structures might survive only around 1,000 years before collapsing. Larger dying stars tell a completely different story. Around red giants, a swarm could last 5.3 billion years. Around red supergiants, that number stretches almost beyond imagination. So stability itself becomes another clue in the search. Scientists are careful to stress what this research does not prove. This study contains no direct observations and no confirmed candidates. It only offers a map of where and how to look. That distinction matters enormously in real scientific research. But it also means this search just became genuinely possible. Somewhere out there, 5 unexplained stars are still waiting. And for the first time, we finally know how to look closer.